All right, chemistry, this is your video lecture for Chapter 5, Section 2. Still talking about the periodic table, but we're going to bring in the idea of electron configuration to the way that the periodic table is set up. Now, there will only be one video lecture. This is not broken up into two parts because, again, this is a pretty short section. So far in Chapter 5, Section 1 has been pretty darn short. Section 2 is going to be pretty darn short. Section 3, however, is going to make up for all that slack. So just get ready during the next section. What we're trying to accomplish for this section, here are your goals / questions that you need to be able to answer in order to satisfy those goals. Without looking at the periodic table, not looking at the periodic table, just in your head, give the group, period, and block in which the element with the electron configuration xenon 6s2 is located. Just based on that noble gas notation, give me the group, period, and block. Secondly, again, without looking at the periodic table, just from the information I give you here in this question, write the electron configuration for the group 1 element in the third period. Is this element likely to be more reactive or a less reactive element than the element described in the previous question? Okay, so if you can do both of these things off the top of your head, you will have satisfied my goals for you for this section. All right, let's get started. Let's start with the S block. The S block are known as the reactive metals. They're composed of groups 1 and 2, including helium. Now, the only thing I want to point out about hydrogen and helium as part of the S block, they are truly part of the S block. We have hydrogen on top of group 1. We have helium way over on top of group 18, is still considered part of the S block. They are not actually metals. Okay, they are non-metals. They are truly non-metals. The only reason that they're placed on top of group 1 and then they would be a part, and then helium would be part of the S block, is because they have 1 and 2 valence electrons respectively. So the S block looks like these two groups I have over here on the far right side, hydrogen down and helium down. Let's look at group 1 specifically, the alkali metals. Yeah, alkali metals, group 1, they're known because they all lose 1 valence electron. Remember, Mendeleev ordered his elements, or should I say he grouped them in terms of similar chemical characteristics. This group here has similar chemical characteristics. Why? Because they all lose 1 valence electron, which means they're all reducing agents in the same way. Because of that, or what that means for how they operate in nature, is that they react violently with water. They also react with halogens to form salts. Now, you guys know what halogens are right now. You don't know what salts are in terms of chemistry, but you will in the future. Moving on to group 2. That has a typo. This should be the alkaline. Should be an N and an E there. The alkaline earth metals. Group 2. Now, they are in group 2. What that means is they have similar chemical characteristics. They all act in the same type of way. The reason being is that they all easily lose 2 valence electrons. I don't know if you've noticed the pattern here yet. Group 1 loses 1 valence electron. Group 2 loses 2 valence electrons. Now, they're still very, very reactive, just not quite as reactive as group 1. Group 2 elements tend to be harder, denser, and stronger than the group 1 metals. And because of that, they tend to have higher melting points. Okay? It needs to be a lot hotter before they melt from a solid into a liquid. And again, they are less reactive than group 1, but they're still far too reactive to be found free in nature. You never just find a chunk of calcium or a chunk of strontium in nature. They have to be purified from other binary compounds. All right, now let's take a look at the transition metals. Again, these are the D block elements. You're going to find them in groups 3 through 12. Okay, these groups are not considered main groups. This is just groups 3 through 12. The transition elements are metals with typical metallic characteristics, often called transition metals. Now, when you talk about metals, what people commonly think of are things like gold, silver, platinum, copper, iron, chromium, titanium. These are the typically metal things. And so when people think of that hard, shiny type of element, this is actually the type of element they're thinking about. That's why we say these are the typical metallic properties. They're actually transition metals, transition elements transitioning from the metals side of the periodic table to the non-metal side, which is more the right side. We'll call these transition metals. Now let's take a look at the remaining main group elements. Again, like I pointed out in the last slide, the D block, groups 3 through 12, those are not main groups. They're just considered groups. But when we talk about main groups, we're talking about groups 1, 2, and then 3 through 18. All of those are main groups. Those are main groups. So we'd look at the remaining main group elements. We're going to be looking at the P block. Okay, those are the only main groups that we haven't looked at yet. That's the P block here. It's composed of groups 3 through 18, excluding helium. Okay, and helium is not part of the P block, even though it's over there on the right side of the periodic table. The P block and the S block elements are collectively known as main group elements, like I've already said. And they are made up of all kinds of stuff. They are made up of metalloids, nonmetals, and metals. Okay, so there's a huge grab bag in terms of categories present in the P block. So if you look at the P block nonmetals, okay, the nonmetals I have highlighted on this picture in red. These are the elements that are to the right of the metalloid staircase. The metalloid staircase here is illustrated in purple, depending on if you guys are seeing this the same way I am. In the non-metals, you're going to find the noble gases and the halogens. Those are smaller categories. Than non-metal. Non-metal is a large category, has several subcategories. 2 of those subcategories are halogens and noble gases. Let's look at the halogens specifically here. This is composed of elements in group 17. They're the most reactive elements out of all of the non-metals. So out of the non-metals, they're the most reactive. They combine with metals to form salts. Remember, group 1 is going to react with these elements the most violently and the most readily because they're the most reactive. Let's look at the noble gases all the way over there in group 18. Okay, they are the least reactive out of all elements. And in fact, they are some of the most recent elements to be discovered because until recent time, chemistry was studied based on the reactivity of elements. And since these things aren't very reactive, they weren't studied. They were unobserved. Now, the reason that they're so stable comes from this special electron configuration, which is known as a full valence shell. Now, we're going to focus on valence electrons coming up here in a while. Right now, all you guys need to know is that if you have a full octet, a full 8 valence electrons in your outer shell, your highest principal quantum number, you're going to be very, very stable, and that is actually why the noble gases are stable, with the exception of helium, which only has 2 valence electrons, but again, that doesn't have an octet. It's said to have a duet, and that's perfectly okay for helium specifically and only. All right, let's look at the P block metals. Okay, here they're going to be listed in kind of like a teal aquamarine color here. They're to the left of the metalloid staircase. They're chemically similar to the rest of the metals. Okay, they're going to want to react with a non-metal to form a salt. The only difference is the presence of an electron in the P block. That's the only real difference that they have from the other metals. All right, let's see how we've been doing so far. First thing I wanted you to be able to do without looking at the periodic table, give the group, period, and block in which the element with the electron configuration of xenon, 6s2, is located. I also wanted you to be able to write the electron configuration of the group 1 element in the third period. And then answer this question, is this element likely to be more active or less active than the element described in the previous question? So let's take a closer look at these. Give the group, period, and block. Okay, group, period, block. Here we go. Now, this is in the 6s, 6s2. Okay, so there are 2 electrons in the 6s, so that means that we are in group 2, okay, because it's 6s2. Now, looking at that principal quantum number, 6, that means that it's going to be period 6, again, 6s2. And the block is S, right, 6s2. And so these 3 figures in the valence, the outermost electron configuration notation, the 6s2, there are 3 terms, and those are the terms that give us the information here. Group 2, period 6, block S. Go on to our second check for understanding. Write the electron configuration for the group 1 element in the third period. Okay, let's start with that before we consider the more or less active part. So, you're talking about third period. So, n equals 3. Okay, n equals 3. So that means if we got to n equals 3, that means that 1s, 2s, and 2p sublevels are completely filled. Because remember, the off-bow principle says that an electron will fill the lowest energy orbital that is able to fill it. So if we have an electron filling something in the third period, that means everything before it must be filled. So before we get to the third period, everything in the first period and the second period must be full. Now the question also tells that it's group 1. It's group 1, so that means there's one electron. One electron. So it's going to be in something in the form of NS1. If it's group 1, it's in the S block. If it's group 1, there's one electron in the S block. So we've already established that the 1s is going to be full, the 2s is going to be full, and the 2p is going to be full. So that's going to look like 1s2, 2s2, 2p6, and then our one electron in the third period will be 3s1. Or we can write that in noble gas notation as neon 3s1. All right, guys, like I said, this will be the only lecture for this section. I will see you next period.